Okay, thank you very much, Katja, for the introduction. So I'm presenting today's joint work with my PhD student, George, and two other people who live south of the border, so I'm not sure whether I'm supposed to mention them. So this work is about pattern matching in the context of GHC, the Glasgow Haskell compiler, and checking or verifying these pattern matches. And there are two properties that we want to check for. The first property is whether a pattern match is exhaustive or not. So here you have a zip function with two clauses. And if you can just type this in and you can run this Haskell program, and then you get a runtime exception, which is of course not so nice. Ideally, we want to have strong guarantees from our compiler so that if we compile our programs, then if we run them, then we won't have any crashes at all. But fortunately, GHC has this flag in the compiler that can turn on some checking of this pattern match. And if you do that, then the compiler will actually come and tell you that actually this pattern match is not exhaustive. There are two cases here, two patterns for the arguments that are not covered. So this tells you that this function, this pattern match here is non-exhaustive, and you have to think about it whether this is what you want or not. But because you have forgotten these cases, at runtime, you might get a crash when you're calling the function with such values that fit these patterns here. Now, this works fine, this analysis in GHC, until the point that GADTs were introduced, because then the analysis was no longer able to deal with that extension. So here's a small program with a GADT. It's kind of the standard example of a GADT. It's a vector indexed by its length. So you can build an empty vector which has the length 0, or you can build a non-empty vector with an element, a tail of length n, and then the vector you're building here has the length 1 more than n. Okay, so here's the counterpart of the zip function for vectors, and now we require in the type signature here that both input vectors have the same length. Okay, so we're covering in the two patterns to do different cases. We have both empty vectors or both non-empty vectors. Okay, so this is fine, and we run this through the compiler, and unfortunately the compiler will complain, and will say that also in this case the pattern match is non-exhaustive. There are supposedly two patterns that are not covered. A combination of an empty and a non-empty vector in either order. All right, but if you look at the types, none of these patterns can actually happen, right? Because in the type here, we're requiring that both vectors have the same length. And if you look at the empty and the non-empty vector, the empty vector will always have length 0, and the non-empty vector will never have length 0. It will also always be the successor of some other number. So according to the type, these patterns cannot happen. And actually, if you would extend this function with two more cases covering these patterns, the type checker would come and complain and say that these two cases are ill-typed. Yeah, so there's no way in pleasing the compiler here. You will always get these bogus warnings, actually, that should not happen. So that's the problem with exhaustiveness checking of GADTs. There's also another issue with the other property we want to check for pattern matches, and that is whether there are some redundant clauses in the pattern matching, whether there is some dead code there. Consider here a length function that computes the length of a list, and I've added this additional clause here that if the list is not empty and it's not a const list, well then the length is always 42. As you can see, of course, this is dead code, this last clause here, this will never be reached. And
no, length of undefined.
Length of undefined will be caught by the very first pattern here. Because when you call length with undefined, it will try to match undefined against the empty list constructor here. And at that point, the undefined will basically blow up and your program will crash at that point. This is the behavior of Haskell. We are working in the context of Haskell and not in the context of some other ideal language, I'm afraid. So, and GHC will also warn about these kind of redundant cases with this kind of message where it says that this is overlapped. I think it's maybe a bit unfortunate, this message, which should really say that this clause here, length L, the last one, is redundant, and you can safely remove it from your program without changing the behavior of the program at all. So we also want to be warned about these because probably there's some kind of error in the in the reasoning of the programmer when he writes these redundant clauses. So this is good, but in the context of GADTs, this doesn't work well. So I've shown you the zip program for these vectors earlier on. Well, and we've seen that that GHC complains about missing cases. Well, one way to actually shut up GHC is to add this additional clause here where you have two don't care patterns for the two arguments. If you add this clause that can actually never be reached, then GHC is happy and will not complain. But it will also not complain about, so this is a lot of people that have been working with GADTs actually add such catch-all useless clauses to just shut up the compiler. But this is actually dead code. So actually we would like GHC to complain about this additional clause, but it just stays quiet and it doesn't say anything about this. So that's another weakness in the current, in the existing approach of GHC with verifying these pattern matches that we also want to solve. So basically, the analysis for exhaustiveness and redundancy in the context of GADT pattern matches is just broken in GHC. You cannot rely on it at the moment. But actually, while we were investigating this, we came across some other issues, not necessarily related to GADTs, but also issues in these analyses that were not handled well in GHC. And I've got a little quiz for you. I've got here a small program. Well, this one involves two GADTs, F and G, and they both have one index. You have two constructors on both sides. There's one that kind of matches up because the index is both int in the first constructor, and in the second constructor you have two different indexes, bool and char. Okay? So we have this one function, h, that takes value from F and G, both with the same index, and returns an int. And we have two clauses here. Okay? We have one with F1 and G1, and we have one with two don't care patterns. Now the question is this last clause here redundant or not? No. Who says it is not? Connor? Who says it is? One person. The others have no opinion. Okay. So let's see. So we can call this function with these two arguments. One is F2 and the other one is undefined. Right? Undefined basically takes any index value, index type you want. It does not have to be restricted to int and char. It can also take bool as an index. Okay? So in this case, we can actually run the program and get the result 2 using the second clause. Now, if we remove this clause, then this call is not handled. There's no clause covering this, and you will get a runtime exception that you don't want. So it's not safe to remove this clause. If you remove it, then you're changing the semantics of the program. So the analysis has to be aware of this kind of property of laziness in Haskell. Here's another program. So here it's just a function over two booleans, and you have three different clauses that cover different cases. You have a catch-all case at the end. And my question now is this second clause redundant or not? Who says it is not redundant? Two people say it's not redundant. Who says it is redundant? Okay, so let's see. So what happens if I call my function in this way? I have an undefined value and a true value. Okay, so the first clause, it does not look at the undefined value. It doesn't touch the bomb. Okay, so the bomb doesn't go up. And then it compares the second argument true against false. This fails. So what do? We go to the second clause. The second clause, we try to match undefined against true, and our bomb goes off and it explodes, and we get this exception. Right? Now, if you remove the clause, then we never look at this first argument because both the patterns here for the first argument are don't cares. So the bomb never goes off, and we get the result 3. Right? And this is very strange behavior that we discovered while studying this. And so in some sense, this is a useful pattern because it affects the semantics of the function. But on the other hand, there's also something special going on here because with this case, you can never actually reach the body of this clause. You can never execute, you can never get a value 2 as a result. Right? The only effect of this pattern is to force the first argument. Yeah, so this is a kind of very limited usefulness of this clause in forcing this. And this is one of the kind of strange situations that can happen in Haskell. And it's something that we wanted to adapt our analysis to also be able to warn about these situations and to tell the programmer that watch out, the body here is that code, but still the pattern match itself has an impact on the semantics of the function. So alongside that, we also looked at another feature that's called guards, which are also involved in selecting a particular clause. These are these Boolean expressions where you want to check whether x is smaller or greater than 0. And you can ask the question again, is this an exhaustive function? And yes, it is an exhaustive function, but unfortunately the compiler cannot tell. It's just not smart enough. It doesn't look at these guards at all to decide that. And the same for other kinds of extensions of the guard language. There are all kinds of extensions that deal in some way with expressions that have to be reasoned about. So the challenge for us is that we want to have a uniform approach for dealing with all these different language features that are involved in pattern matching and selecting particular clauses in one approach. So there are lots of different works that have already looked at these aspects of exhaustiveness and redundancy in the context of, for example, dependently typed languages, where you want your function always to be exhaustive, of course. But here we also wanted to take into account the laziness and all kinds of language extensions around guards and so on. So our approach is actually of this form. We are going to analyze different clauses in a sequential order. So here you have the patterns of a first clause, the second clause, and so on. And as an input, here we take a kind of symbolic representation of all the possible values that could be fed into this pattern match. And then we analyze this, and we get, for a clause, we get 3 different outputs. We get a representation of all the cases that are covered by the pattern, all the cases that are uncovered, and all the cases where some undefined is exposed and the function diverges. So, so we get an output, the uncovered cases here, and these are the cases that are fed into the next clause, and so on. So at the bottom here, what you get out are all the uncovered cases of the whole function, of the whole pattern match, that are not covered by any of the clauses. So let's have a look at how this works in a concrete setting of just simple, plain algebraic data types, Haskell 98 data
not
types.
abstract data types,
Algebraic data types. Abstracted. Yeah.
Well, ADT, well-known useful abbreviation.
Yeah. So here's our zip function again. So we're going to look at the 2 clauses, and in particular just the patterns. The names of the functions don't really matter in the analysis. And so we're going to process first this first clause here, and we're going to take a representation of all the possible inputs, abstracted over in a finite representation, and this is just this representation. We use this vector of underscores to represent all possible choices of values for these 2 arguments. And then we analyze this input against these patterns, and what we then work out is that, well, the cases that are covered can be represented in this way, just the 2 empty lists. And because this is a non-empty set here, we can also decide that this is actually a useful clause, because it actually matches some values. We also figure out that there are some diverging cases exposed here. In the case where the first argument is a bottom, we never look at the second one. In the case where the first argument is empty and the second one is a bottom. Both these cases will be exposed by this pattern match. And then you have, so this pattern is also forcing some things. And then we have a number of uncovered cases, where the first list is non-empty and where the second list is non-empty. So these are fed into the second pattern match. And again, we do this analysis. And then we figure out that, okay, this clause is actually also useful. It's covering all these cases of this form. It is also forcing particular situations. Is there a question?
Yeah, so this is like a negation elimination in some sense, right? You have a complement set, and you're giving a constructive definition of it.
Yes, I will show you in more detail how we do this analysis shortly. And finally, we have these uncovered cases here, and these are the ones that give rise to this warning that our function is non-exhaustive, because we have a number of remaining cases that are not handled by the two clauses. So we have in our analysis some basic syntax. This is the syntax for patterns. We have don't care patterns, and we have constructor patterns with some arguments here. And our value abstractions are actually represented in the same way, with underscores for any value and constructors for values that are rooted in this constructor. And I'll show you how we do the analysis for one particular output here for the covered cases. We define a function that processes a vector of these patterns and value abstractions, and we get a number of cases. So if we have no more patterns, an empty vector of patterns, we don't have any work to do, so we can trivially return that yes, we have no, in some sense, no values matched, an empty vector of values matched. And then we have the case where we have a don't care pattern at the front of the vector of patterns. Then this matches basically any kind of value. So we go on recursively with analyzing the rest of the pattern, and then we get some representation of all the covered values there, and we just stick our initial value to the front of that.
So why is that not the empty set? First.
This one, because we are indeed covering a situation. So we have an empty vector of patterns, and we have an empty.
Oh, I see.
Yeah. This is different from not matching, yeah, which we will see in the case of the matching against the constructor. So that's the case here. So we have a pattern that mentions a constructor. We have a value that has a constructor in the first position. And then we check whether these two constructors are the same. Okay? If they're not the same, if the constructors are different, then we can see that this will never match. And then we have an empty set of matching cases here. Okay? And in the case the constructors are the same, then we go on recursively with matching the remainder, and then having a representation of the matched values, sticking this again in the constructor in front of that. So there's some kind of juggling going on here, because we have arguments to the constructor and some remaining arguments, and we just flatten this here in the recursive call, and then restructure it again to get the representation. But that's maybe a detail that's not very important now. And we have a last case where the pattern has a particular constructor at the front, and for our value abstraction, we cover any value for the first argument. What we do at this point is we do a kind of refinement. We see that, okay, the only possible, you can choose from all the values, and the only values that can possibly match this pattern are the ones where we have exactly the same constructor at the front. So what we do is a kind of refinement of this value abstraction, and only picking out the ones where we have the constructor at the front. And then we recursively call the coverage function to deal with the case where you have the same constructor in both the pattern and the values. So this is essentially the analysis for the covered cases. And in a similar way, we're processing in lockstep also for the uncovered and the diverging cases, both the pattern and the value abstractions, and refining the value abstractions as we see more of the pattern that we're trying to match. Okay? So this is the basic approach. And now we've developed an extension to also deal with GADTs. This is kind of refinement of the approach. So with GADTs, you have these indexed data types. And so I've used this representation in the example, where the index, the NAT index, is refined here in the result types of the two constructors. But another equivalent representation that you can use in GHC is this one, where the index type here is not refined, but we explicitly write this kind of type constraint, this equality constraint, over the index type to state the refinement. And it's this kind of type constraint representation that we're going to use to reason with. We're going to collect such constraints and reason about them. And what we're going to do is we're going to refine our representation of values, our abstraction of the values. Before we were just using these kind of patterns, but now we're going to augment this. We're going to have so a vector of value abstractions together with some constraints. So you can have any values that are covered by this abstraction here, but they also are subject to these type constraints. Yes, and the type constraints are essentially these equality constraints over the types that refine some of the index variables potentially. And we also need an oracle where we can give a bag of these constraints to the oracle, and the oracle will tell us that these constraints are not satisfiable, or the oracle will say maybe the constraints are satisfiable. I'm not sure. That's what we need as well in our analysis. And then we can analyze the zip example for the vectors, where again we have an input that covers all the values, and they are unconstrained. So we have this epsilon here, which represents an empty bag of constraints. So any values, any choice of the index types is possible. And then when we check which cases are covered, then we get these refinements here that say that, well, the index variable for both pattern matches has to be equal to 0. Okay? What we would do then is we would give these constraints to the oracle. The oracle would say, well, maybe these constraints are satisfiable, and then we would not know that. Then we would think that maybe there are some values here covered by this representation. So possibly this case here is useful, covering some cases. So similar thing happens with the uncovered, with the diverging cases. So you get, here you don't get any additional constraints, but here you get one from the first pattern and nothing from the second pattern. So we have two uncovered cases by the first clause. The first case here is not matching the cons constructor with the nil constructor, so we get this refinement from the cons constructor that says, well, okay, the index actually is the successor of some other natural number n. And then we have this, the second uncovered case is an interesting one. So we have a nil constructor and a cons constructor, and you get two constraints from this refinement here. From the first one, you get that the index has to be 0, and the second one says it's non-zero. Okay? Now, if you give these constraints to our oracle, then the oracle will tell us this is actually inconsistent, and that means basically that this particular case here is not covering any values at all. Okay, so we can just remove it, and we can go on with a smaller set just with the first case here. The second case does not represent any values at all. So we can feed this remaining case, uncovered case, actual uncovered case, into the second clause. We analyze again. You get, again, some covered cases, some diverging cases. And at the end, you get one uncovered case, cons and nil here. Again, you get basically inconsistent constraints. And this means you can remove this, and you end up with an empty set. And that's good, an empty set, because that means that actually our function is exhaustive. Our oracle is now helping us in deciding this by keeping track of these type constraints, and we can conclude, and we don't have to issue any warnings about non-exhaustiveness, making all the Haskell programmers happy that we're complaining about this problem. So lots of people before, what they did actually was add another catch-all clause at the end with the underscores. And of course, if you feed in an empty set, then you get nothing out. And now we can actually say that this catch-all clause is redundant because there are no covered cases. This is an empty set here. And we can say that they should not have added such a clause at all. So they can all go and fix their programs and remove this catch-all clause. Then we have a third extension, which is to deal with guards. And for guards, we need to extend our approach again a little bit. So here we need to deal with these kind of Boolean expressions. That, for example, x smaller than 0 and x greater than 0. And so we refine the language of patterns a bit to deal with these. So in addition to the two patterns that we had for any values, I mean, we're now using actually variable names to refer to them, and the constructor patterns. So these two patterns are matching against arguments, but we have also introduced a kind of pattern guard, an additional kind of pattern that is not looking at the arguments, but it's just evaluating an expression E and checking whether the result matches the pattern P. Yeah? So for example, I've desugared here the absolute value function, which now in addition to the argument x, the pattern x, also gets this pattern guard here that computes a result for x greater than 0 and matches this result against the constructor true. The same for the other guard, also a pattern guard that matches the result against the constructor true. Okay? And with this particular kind of core representation of guards, we can handle a lot of different situations that arise in the GADT version of the Haskell language. For example, you can have these literal patterns, like the literal 0 here. Well, the way this is actually dealt with, this can be desugared as a pattern guard as follows. So we basically just match on a variable x, and then we have a pattern guard that checks whether this x is equal to the representation of the literal 1 in the type A. So we call from integer on 1, this gives us a value of type A, which we compare against x. And then we check whether the result of this comparison matches the constructor true. So, and this is kind of important to do it in this way, in the middle of pattern matching, because we have two patterns, one after another. You have the 0 here and the nil constructor there. Yes, and you don't want to defer this check until after all the pattern matches, because this happens before you're looking at the second argument and trying to match it with the nil constructor. Doing it in this order is important because Haskell is a lazy language, and you may expose at any point a bottom, and you want to do it at the right, with the right argument first. Another feature are view patterns, and view patterns work as follows. So this is a view pattern where you implicitly match an argument and you call the toRadians function on it, and then you look at the result and you check whether it matches this particular pattern here. So this we can also desugar into this representation where we first explicitly match against the variable x, and then we use this x in a pattern guard to compute the result and match it against this tuple here. So and in our paper you can see a number of other language extensions where we deal with, in the same way, desugaring them into this pattern.
Is that first example, the 1 is supposed to be 0, I think?
Yeah, sorry, it should be 0 indeed. Yeah. So that was a refinement on the side of the patterns. We also have a refinement on the side of our value abstractions. So remember, we had value abstractions where they are subject to some constraints. And up to this point, we only had these type constraints, type equality constraints. But now we also introduce term level constraints. Okay? Constraints that say that a particular value has to be equivalent to an expression. And similarly, for the divergence, we have these constraints that say that a particular value, a particular variable diverges. So these are additional kinds of constraints that we can now talk about and that our oracle should reason about. So here's, for example, the clause for the abs function, the first clause, where we feed in all possible unconstrained values. And when we match against this clause, we get a number of covered cases. And these covered cases are the ones where we introduce a fresh variable y that should be equal to this expression x smaller than 0. And we also get the constraint that this y should be equal to true. In that case, these are all the values that we are covering with this clause. You get something similar, but here you get divergence of y for the diverging cases. So if our guard computation diverges, then we have a divergent case. And then we have the uncovered cases. This is where the result of this guard is basically equal to false. Then we go into the second clause with this set here, and we get a bunch of additional term level constraints. We have the result of the other guard is called z, and z has to be equal to true. Then these are the covered cases here. We have some diverging cases where z equals bottom, and then we our oracle can actually do some reasoning here. If it's smart enough, you can see that, well, if x smaller than 0 is equal to false, then it cannot possibly happen that x greater than 0 diverges. So our oracle could be smart enough to reason about this and tell us that there are actually no diverging cases anymore in the second clause. And finally, here you have the cases where x is both greater than 0 and smaller than, there should be a smaller than 0 and greater or equal than 0. And again, if our oracle is smart enough, then I could see that actually this is just the empty set and there are no uncovered cases. And this function is actually, exhaustive. Right. Okay. So this is basically the approach that we have taken, this analysis clause by clause with these value abstractions. And so we've implemented the prototype in GHC. You can get it in a separate branch. We're working at the moment on a stable release. And it's actually a very small implementation. For all these additional features that it has, it's actually a little bit smaller than the existing implementation that did not cope with all these cases like GADTs and GADTs. We have implemented, in a way, a simple oracle. Well, it's very powerful for types because the type level oracle for the type constraints is actually just a GHC type checker that can answer basically perfectly for the type level constraints. But at the term level, we have at the moment only a weak oracle that's good enough to deal with trivial cases like a guard that is true or otherwise, so it's very simple at the moment. So there's still a lot of room for improvement in this area, doing smarter reasoning there. And then we have analyzed the behavior of our new approach on a number of packages. We have asked people who are using GDTs and that had problems with wrong warnings. We asked them to tell us about their packages, and so we have collected a bunch of these packages. And we've compared actually 3 different systems. There was the original approach of GHC, and already at some point people were complaining, and there was a kind of ad hoc patch implemented to deal with some of those cases, suppressing some of the warning messages. So we're also comparing against that, and then there is our own approach. So these are the libraries with checking problems. Most of them you can find on Hackage. So to start with, here in this column, you see all the clauses that have erroneously reports of missing clauses. So the compiler says, okay, these pattern matches are not exhaustive. There are some missing clauses, but these warnings are actually bogus and they should not be there. And you see, for some of those packages, you get lots of these warnings. And basically, people just start to ignore the warnings because they're all wrong. And actually, so the patch that was introduced, this ad hoc patch, was quite successful at suppressing a number of these warnings. You only get in 2 of those packages some remaining warnings. And with our approach, we were able to actually reduce these warnings from 9 to 8 and from 42 to 16. So why do we have these remaining 8 and 16 there? Because we're also including in these numbers cases where GADTs are involved. And we have only a weak reasoning over GADTs, so we're not able yet to deal with those cases. The situation is quite different in terms of the clauses that are actually not reported redundant. Reported redundant. So in this case, there are lots of catch-all clauses that are not reported. So you see all zeros here, where we would actually expect some warnings to be issued. And the ad hoc patch has no impact on this whatsoever. There's no improvement. But with our approach, we're actually able to expose all these catch-all clauses that people have added and that they actually should take out because they are redundant. And we can tell them now that they are redundant. So that's basically the evaluation that we've done at this point. So you see that there's still already quite a bit of improvement here. And it's in particular important to get rid of these catch-all clauses because they're very dangerous when you're extending your program. If you're adding more constructors to your data type, you want to be told by the compiler to which of the different functions you have to go and add more cases in. But if you have catch-all clauses, they will already be captured by these clauses, and you get no warnings whatsoever, and it's very hard to attack your program. So this is very important. There was also a concern about our value abstractions. We use this set representation that we kind of gradually split up as we refine and go through the pattern matches. And potentially these sets could blow up and make the compiler very slow. Yeah? So we were wondering whether this actually happens in practice. And so we looked at all these different packages and looked at how big the abstractions, the sets that we use in these abstractions actually get. And so here you see 3 different categories of modules or pattern matches where we have different sizes of the sets that we're looking at, covered or uncovered sets, the maximum size. So most of the programs, like 97.9 of the pattern matches, the sets are very small, smaller than 10. And so there are a reasonable number of cases where the sets grow up to a size of 100, about 2%. But still there are a few outliers that are extreme. There's some packages where things get really big, more than 1,000 elements in this set abstraction. And that does really slow down the compiler. So in actually all of these 5 cases were all in the same package. There was one programmer very keen on this kind of situation, where they basically have functions of this form. So you have a data type with a number of constructors, and you match on 2 arguments that both should have the same constructor. And this exposes the kind of worst case scenario where your sets really become big. And in fact, in this case here, the largest case that we found, we had a data type with 54 different constructors, and so a function with 54 of these different clauses. So in practice, your compiler has to also be resistant against these cases and kind of bail out at some point and just give up if the sets become too big.
Just punishment.
Yes. So all in all, we think that our approach is fairly workable. You just have to be careful with these problematic cases that don't happen very often. So yeah, this is already the end of my talk. So what I've presented is that we have a uniform approach to deal with different language extensions. In the verification of pattern matches, we can deal with GADTs, laziness, and GARDs, all kinds of extensions of GARDs. And it's going to be very soon part of a stable release of GHC. So we have a paper, and you can see the whole description of the algorithm if you're interested. We present a number of optimizations, both to optimize our algorithm itself, but also to use the results of the algorithm to do some optimized compilation. There's also meta theory in the paper and lots of related work. There are lots of other people that have already looked at pattern matching in one way or another, so this is a very well-explored field. And we're adding another story to this. Okay, thank you very much.
Thanks, Tom. Any questions?
In terms of making the Oracle smarter, do you think it will be easy to get candidates to cover the most cases that people will encounter, or do you think that there might be areas where the library might need a little bit more work?
So I think there are some off-the-shelf solvers that we could plug in that reason about SMT solvers, for example, that have theories about particular domains that we could, for example, use to reason about the greater than and the smaller than of natural numbers. These kind of cases that would be very cheap to plug in. I think what would be harder would be to reason about arbitrary functions that have been written by the programmer and constructors. I think that's for me still kind of an open question how to deal with those situations.
Coming back to slide 35, which had all the numbers.
Right. Okay.
What happens if the code has all the capital clauses removed?
What happens? We didn't do that, but then.
But you presumably then get rid of all these R.
Yes, you get rid of all these ones. Yes.
Yes. Would the M's go up?
The M's would not go up, no.
Right.
Yes, because all M's are basically the numbers we have here are bogus warnings.
Yes.
Yes, but that would not go up
You wouldn't
because we can now appropriately deal with these situations. Yes. Yes.
So you said in practice it didn't seem to matter that you might get a blow up in the number of these uncovered and covered cases. But presumably there might be some way of optimizing your algorithm if you did care about that.
Yes, and we have some description in the paper how to optimize the algorithm to deal with that and kind of do some sharing,
Yes.
so that you don't. Yes, but in the extreme case it's still pretty big, and so these bottom cases here, you still have to have an approach to deal with them that does not blow up the runtime.
Right. But do you think it would be feasible to?
You can never deal with the worst case. The programmer
You
can
can always
always
come up with a contrived case.
yeah throw something at you that you cannot deal with. Yeah.
So your GADT example is actually GADT plus data kind, right? Do you have the same kind of errors with just GADT?
Yeah, the data kind is not really relevant. I just wanted to show it in the nice form, but you can just replace the nat by a star and then you get the same issue.
Even with the adduc hash?
Yes.
So there's a notorious issue that even if all of your indexing for GADTs is nicely in constructor form, but certainly in the total setting, exhaustiveness checking is undecidable. You can code up the halting problem,
Yes.
and I did on one page of my thesis.
Yeah.
So I'm wondering what the status of this checker is. Is it does that problem somehow disappear because you always have to worry about undefined, or is it just a question of how clever is the constraint solver, or where does that problem go?
Right. So it goes two ways, I guess. I mean, one issue is at the type level with these computations. Sometimes you don't have enough information to decide, and then as our oracle, we use the type checker, and the type checker just says maybe this is satisfiable or maybe not, and we can live with that. So we don't try to be smarter than the type checker at this point. And then there's the other issue of at the value level. So there's again kind of the issue of the oracle reasoning about arbitrary expressions, which at the moment we don't do, so that problem doesn't go away. But there's also the issue whether particular GADTs are inhabited or not, and the situation is different from Haskell compared to total languages, or compared to strict languages as well, like OCaml, for example, where certain GADT types are not inhabited, because there's no constructor that deals with a particular refinement of the index. But in the case of Haskell, we always have undefined, so we don't. It's in some sense easier for us that we have undefined. But on the other hand, in our analysis, we have to track it as well. Yeah.
No questions? Let's thank our invited speaker again.